Can you hear me? Hello. This is the third lecture on the project on elephant random walk. In this lecture, I will talk about strong approximation technique. And in the second part, I will present some of our results on variation of elephant random walks. Let us recall the definition of standard elephant random walk. Yesterday, Rahul talked about variation, but this is the uniform memory case. The elephant chooses one of its previous step uniformly, and with probability p and the same direction, and otherwise the opposite direction. It is a kind of Fourier scheme with random replacement. And we rewrite this conditional distribution like this, and introducing a new parameter alpha, and this is between -1 and 1. Then we obtain a convex combination of reinforcement part and ordinary random walk part. Using this distribution, we can obtain the conditional expectation of the increment, and it is given by the position of elephant. And adding both sides, adding Sn to both sides, then we obtain this nice relation. Right? Using this latter relation, we can compute the expectation with the position, and this is of order n to the power alpha. So if something happens at alpha half, actually, if alpha exceeds half, then the second moment grows superlinearly. And corresponding to this behavior of the second moment, we obtain several limit theorems depending on 3 different regimes. If alpha is less than half, then the scaling is exactly the same as the ordinary random walk, and in the limit we obtain the Gaussian distribution. And in the critical case, the limit is still Gaussian, but the scaling is slightly changed. Log appears here. And in the supercritical situation, the scaling is now n to the power alpha, alpha larger than half, and we obtain some non-Gaussian limit distribution. The next, on Monday, I skipped the next slide, and I will give some comment now. Not so many properties are known about this limiting variable, but Guérin, Laurent, and Rachel, and independent Queen shows that the distribution of L is absolutely continuous, and in particular, it is not 0 with probability 1. This scaling is correct. And in the subsequent work by those 4 people, they derived the asymptotic behavior of the density function of this variable. If the first step probability is half, then L is positive and negative, each with probability half. And this is a numerical calculation of the distribution of the elephant. And alpha exceeds half, then we can observe two peaks here and here. Okay. Now non-Gaussian variable appears in the supercritical case, but if alpha is between half and 1, then the fluctuation from Ln to the power alpha is still Gaussian. This term is a random drift induced by step reinforcement, memory effect. And subtracting this random drift, then we recover the Gaussian distribution. So those limit theorem explains some of the feature in this graph. I mentioned some of limit theorems for the elephant random walk, and I present one more. And this is about the scaling limit in the subcritical case. In this case, elephant random walk is believed to be similar to the ordinary random walk. And actually, by diffusive scaling, this process converges to some centered Gaussian process, and its time correlation is given by this function. This result was first derived by Bauer and Bertrand. They used the Poirier approach and used one result in a big paper by Jansson. And what is this GT? And later, in a different paper by Bertrand, GT can be written, represented by this stochastic integral. And computing the variance, this is nothing but time change the process of Brownian motion. And Bertrand, in the paper by Bertrand in 2021, he considers only positive alpha case, and he called this process noise reinforced Brownian motion. But in the standard elephant random walk case, alpha can be negative, and GT is still well defined. But for negative alpha, GT has no name. So you can name it if you want. Okay. So there are several ways of obtaining those limit theorem, and today I'd like to explain strong approximation approach. Strong means almost sure or pathwise approximation like this. Sn is Gn plus some remainder term. This is much smaller than a square root of n. If once we get such an approximation, it gives us many limit theorems, including LNL, CLT, and LIL. First of all, we start with the usual Doob decomposition. Sn is the standard elephant random walk, and its increment delta sk, which is nothing but xk. we have the expectation, conditional expectation is like this, and the first step is special. And in the loop decomposition, we subtract this conditional expectation and centered, and we consider centered version. And this difference is uniformly bounded. And using this martingale difference, we obtain mean zero martingale with mean zero martingale NN. So we can expect this NN is quite similar to ordinary simple symmetric random. Actually, for some delta, there exists some delta, and NN is Bn. This is standard Brownian motion at time n, same n. And the remainder term is much smaller than square root of n. Such an approximation can be obtained the famous Skolhod and Strassen embedding scheme. And this time, in our case, the martingale is quite simple, so we can construct embeddings times very explicitly. Okay. So for simplicity, and I like to explain the independent case first. This corresponds to elephant random with alpha 0. T0, we let T0 0. This is the starting point. And we inductively define Tn, random time Tn. This is after the first time after Tn minus 1, and the Brownian motion comes to the next integer point. So from the distance from the previous integer point is 1. Then the sequence of Btn has the same distribution as the simple symmetric random walk. And this Tn is random, but this is a sum of IID sequence with mean 0 and variance 1. So by a slightly sharper form of low large numbers, we obtain Tn is n plus a small order of n to power 1 minus something. Then the difference between Btn and Bn is like this. And you can see this is much smaller than square root of n. Okay. So this construction can be extended to the standard elephant random.
What is
Some positive constant. Sorry?
What was delta originally? Like you were writing square root to delta.
Every positive constant is okay. Some delta. Some delta.
Okay.
If we can find some positive delta, then it is useful. Anyway, it is enough to ensure this is much smaller than square root of it. In the general case, we subtract the conditional expectation. The first step is a little special, but anyway, we subtract this one. And after that, we put this term. Then, and this is the conditional expectation of delta nk. And this construction gives us this such embedding. And again, if we obtain slightly sharper Lagrange numbers, then BTN can be approximated by BN with sufficiently small remainder error term. In the previous slide, I mentioned the limiting process of elephant random walk. Now, let me give a heuristic for finding the limiting process. The equation number one is nothing but loop decomposition, but I put delta k here. Delta k is just one. This corresponds to the SDE for should be this should be the SDE for the limiting process. Just comparison. And adding SK1 to the first equation, we obtain such equation. And to remove this factor, we introduce AK. This was introduced also on Monday. Then we have this simpler equation. In the Monday lecture, I write this fraction by MK. And this equation corresponds to another form of SD. Then we can find the form of limiting process. And in the expression of SN, we have an additional term, and it is of order n to power alpha. So if alpha is less than half, then we can expect SN can be approximated by GN. By the way, this this another form of SDE can be found as follows. Multiplying by t to the power minus alpha, then we can obtain this, like Bernoulli's differential equation. Okay. This is just a heuristic, but we can make it rigorous. Sketchproof is not rigorous, but can be made rigorous. So using equation one, then we obtain this form. But in the right-hand side is SK contained. So this is quite different from GN, but the idea here is to introduce the intermediate process called GN bar, like this. NN is similar to BN, and SK replaced with GK bar, and ignore this term. Then, for our purpose, it is enough to show that both GN minus GN bar and SN minus GN bar are quite small compared with square root of n. This strategy is found in Bai, Fu, and Chan. this paper is concerning a very generalized version of Fourier type scheme. Okay. GN and GN by is quite different, but let us look at this difference. This still not so similar, but expanding this, then we obtain somewhat similar expression. Using this and do some computation patiently, we can show that the difference between Gn and Gn bar satisfies such equation. And on the other hand, how about Sn and Gn bar? This is similar, and difference about the difference satisfies this equation. So those equations looks very similar. So finally, we use this simple lemma for deterministic sequence. In the previous slide, there are two equations, two recursions like this. Then the general term Qn can be represented by this sum with the coefficient satisfied this bound. In particular, this error term is small order of this one, and alpha is the parameter alpha is smaller than this exponent. Then Qn is also small order of the same quantity. And there are several ways of approximation that I explain here, one of them. And this is about subcritical case, but similar strategy is applicable also for supercritical case. And let us recall the CLT. In the subcritical case, the limiting variance is this one. And this supercritical case, subtracting this random drift term, then we obtain 2 alpha minus 1 reversed. So I'd like to explain why this variance appears. So for this, in the supercritical case, we use equation 3. This 3, which is equivalent to another martingale introduced on Monday, and this has very simple expression. And if alpha exceeds half, then this sum is finite, and by the martingale convergence theorem, Mn has a limit almost surely, and in L2. So to find this difference, first we consider the difference between Mn and the limiting M infinity. This is minus tail sum of this one, and then we approximate this difference by a difference of 2 different time of Brownian motion. And in this case, we obtain this kind of error term. And doing similar calculation as before, we obtain this kind of strong approximation. This time, the interval for stochastic integral is n to infinity. And this strategy is found in recent preprint by Li Xin-Chan. Li Xin-Chan. So anyway, in the supercritical regime, such a strong approximation holds true. And by the way, alpha is between half and 1. Then this process has the same distribution as this one. The parameter alpha 1 minus alpha and n to infinity to 0 to n. This why this is true? Computing the variance, the left-hand side has the same distribution as this process, and using the time inversion of Brownian motion, we have this equality. This is outside and reverse. And rewriting this a little bit, then we obtain the right-hand side. So that's why those two limiting variants appears here. Okay. This is the first part of my talk, and I hope this strong approximation technique is useful also for several variants of elephant random walk. In the second part, I will explain one of them. Today, in the second part, I will talk about the elephant random walk with limited memory. In the standard case, the previous step is chosen uniformly. But in here, we make some limitation, the distant past only or recent past only. Now, the first one is about the distant past case. Fix some n, and the definition, the formal definition is very complicated. But anyway, this elephant uses only the first m steps. Then this elephant is essentially always ballistic, and SN over n converges to this this random variable. The special case m is 1 is nothing but the standard elephant random walk with the parameter 1. The elephant repeats the first step forever. So Sn is just n. And the m distant past using first m step, similar. It exhibits very similar behavior. So in this sense, this elephant has supercritical phase only. And on the other hand, if the elephant uses only the m recent past steps, then Xn is m step Markov chain, and this by some mixing property, the elephant is quite similar to the ordinary random. The special case M1 was used in user Pro Nakano's talk yesterday to study continuity property of Takagi function. So for this model, the elephant has subcritical phase only. So how about elephant random walk with gradually increasing memory? So very roughly, to determine the increment xn plus 1, the elephant use the steps x1 to xmn, but mn goes to infinity. Yeah. This model is called in our paper the linear setting, and in the project in this workshop we are discussing about this setting. Those several variations of elephant random walk was first studied by Gut and Tanemura, and such a question was posed, according to their paper, such a question was posed in their 2021 paper, but this quite a rough explanation, just more subtle. And in the newer paper by them, they obtained CLT and other distributional convergence results for the case, very special case. The density of this set goes to 0, negligible. And they gave a conjecture. Similar results hold for the limit between 0 and 1 also. And some more general elephant random. After that, Rahul, Hideki, and myself gave an affirmative answer and obtained some additional results not mentioned in their paper. Okay. In our paper, the problem considered in our paper is different from this linear setting and called in the triangular array setting. I use xn and sn for the standard elephant random walk. And later we will couple this standard process with the new process. Mn is just the same sequence. Mn is between 1 and n and goes to infinity. And in this case, first we fix the final time n and construct the increment ynk. First, mn steps, we use the increment of the standard elephant random. So this we fix this xn first, then we construct the triangular array version. And using those first mn steps, we construct the later steps denoted by xnk. This is chosen uniformly over these mn steps. Then we, using those increment, we define random walk. And actually, we look at the sequence on the diagonal EM. But now there is one remark. Tn is no longer the nearest neighbor random in our setting. But the special feature is it is explicitly coupled with the standard elephant random. So it is useful for comparing those two processes. Okay. Now I present our result. Let me use the same parameter p and alpha and assume that mn over n converges to some gamma. Then for this model, the critical point for alpha is still half. It remains unchanged, but the scaling is different. This blue part. So in the subcritical case, the correct scaling is like this. And if mn is very small, then the correct scaling of the random walk becomes bigger. And critical case, log factor appears. In the original paper by Gut and Tanemura, they obtain such a result for gamma 0 case only. And in the independent and almost simultaneous work by Aguech and Elmachkori, they obtain the same result by a quite different method. And in the supercritical case, this non-Gaussian limit exists. And using the same L, we can show this result for the new process. Using this new scaling, we obtain this non-Gaussian variable. And subtracting this random drift, then we recover Gaussian processor and Gaussian fluctuation again. One feature of our formulation is like this. We can derive those CLT from the results already obtained for the standard elephant random. For example, Aguech and Elmachkori did many calculations from scratch. So for array version of other variant, then we have to compute everything from scratch. But in principle, following our formulation, we can obtain the array version quite easily. And this is distributional limit theorem. And finally, I mentioned one almost sure result. So if p is between 0 and 1, then this strong law of large numbers always holds. And in fact, we have a slightly sharper estimate. If C is greater than this value, then the limit is 0. So this is much weaker than LYL, but in this case, in our model, two different process is combined each other. In such a situation, it is difficult to obtain LIL-like result. So I hope the strong approximation approach explained in the first part will be useful for attacking this problem. Okay, I stop here. Thank you very much.
Yes, I have a question about the stochastic integral that you wrote down for the Gaussian process GT. So how can you write down? Is that a guess? Like, or how do you derive that?
A guess. This one?
Yeah. So it's a guess.
At this point, this is a guess, but using those key equations, we can make it rigorous.
Okay, thanks.
Thanks.
Can you explain the embedding in the Brownian motion again?
Yes. This one? General case.
Maybe not the general case.
No, the simpler case. Okay. Okay. This is the construction. We look at the time, random time. Brownian motion comes to some integer point. So we Brownian motion seek the next integer point. Okay, and then we compare. We want to compare with Bn and Sn.
Okay.
So so we have to estimate the difference between Tn and N.
Okay.
It is a kind of this is done by a kind of law of large numbers. So the basic case, it is small order n to small order n.
And we know what delta is. Delta is something fixed.
Delta is something.
Okay.
Okay. For the moment, if we obtain such an estimate, then the difference between Brownian motion.
And now the general case?
General case. Almost the same. We have to subtract the conditional expectation. This is a conditional expectation.
Okay. Okay. So, and the rest is similar.
Similar. And if we can estimate this difference by a kind of law of large numbers, then also we can also obtain.
Okay, so my question is that is the elephant random walk important here? Like, can you do this construction for in a more general setting, like for a like more general martingale kind?
Yeah, this construction is applicable for so-called binary splitting martingale. So conditional up to time n minus 1, the possible value is at most 2.
Yeah.
And this, based on this construction, we can construct the embedding scheme for L2 bounded L2 square integrable martingales.
So here you have this Tn equals infimum of, and here you have plus minus 1 minus alpha times something, right? So in the general case, this should be replaced by something else, right? Instead of this. And
just this is the basic case, and we can construct step by step.
Okay.
So first we approximated L2 random variable by such a sequence. For a single random variable, we can find that stopping time expressing that random variable. And repeating that procedure, we obtain the sequence of suitable stopping times.
Okay.
So
Yeah.
the details are found in, for example, in the Krenke's textbook. So please.
Okay. Thank you.
Thank you. Thank you.